So I hope you can all see now, as usual, my screen. And organize. Right. All right. So what we want to start doing today is, well, modeling financial markets in discrete time, and trying, or well, at least we start to trying to understand how we can formulate models, and what assumptions our no arbitrage principles are fulfilled, right? So we wanted that the underlying financial model is reasonable in the sense that there is no arbitrage on the financial market. So this brings us to chapter 3, which is financial markets. Right. Well, modeling financial market would be more precise, and no arbitrage. Okay, so well, let me start. Directly with section 3.1, which are financial markets in discrete time. So the first thing is, it's a bit. So what we want to do somehow now is to formulate mathematically rigorously the ideas we have already developed in the first section. So in the section for the foundation of mathematical finance, we thought about how we want to model the financial market. And now with the tools from probability theory like heuristic process and conditional expectation, we are now able to rigorously formulate it in mathematical terms. So the setting, this is basically the setting for the rest of the course, is we start with a probability space. So we consider a probability space omega f p, and we want to equip this with the filtration. So these models are information flow. Space. And well, we do everything in discrete time. This means our index set here are the numbers 1, 0, 1 up to a terminal time capital T, right? This means we have a finite time horizon. And well, each time step here corresponds to a trading time. So we can trade at time 0, 1, 2, 3, up to time capital T. Okay, so that's actually all right. And now we want to formulate the financial market. So the financial market we are considering consists of a bank account and D-risky assets. So this is your short writing for heuristic process in D+1 dimensions. So these are the price, so the price evolution of our assets, which we can buy and sell. So this is of D+1 assets. And what we want to assume well, now we have the probabilistic tools at hand, and we assume that this year is, well, this is the set of prices. So these are D, it's a vector consisting of D prices indexed by time. And this is a D plus positive or non-negative real valued process, which is assumed to be adapted to the filtration. And well, process. And when we think about these are the stocks or assets. So this here corresponds to the risky assets, which is the price evolution of some shares of a company, like traded at the Dow Jones, DAX, or London Stock Exchange, right? So this is some of the risky part in our financial market. And then we assume that there's a bank account which corresponds to the idea of a bond market, but we accumulate it to one single asset because this is not the focus of this lecture here. So we say, okay, these are in a certain sense risk-free. So we assume that they're strictly positive. So this means there's no default risk. So if we buy or sell, or if you buy such a bond, we know there's no default, so the price stays strictly above zero. And to make our life simpler, because we think here we have anyway a finite time horizon, so we like to think of this as a deterministic process. Right? And this is saying if we have a time horizon of say 1 year, we assume that we somehow have a good enough forecast of the interest rate development on a market so that we can basically assume it's a deterministic known process. So this is. Right. So I think, this is what we have already discussed. So this is our risk-free asset. Right. Okay. And now we make the assumption, namely that, well, we wanted that the prices on the market reflect the information. So what we want to assume additionally is that the filtration here is assumed to, so we want that the filtration is actually generated by the filtration, by the risky assets. So this is, so at time t, the filtration ft is generated by all the prices up to time t. Right? So that we assume that the price process is adapted is rather trivial because, well, here we directly assume that the filtration is here generated by the random variable itself. And this is the natural filtration as we have seen. So this is the minimal filtration, which turned the risky asset into an adapted process. Right. But well, in a more general modeling, one could assume that this filtration is even bigger. Say you have some extra information which are publicly known, but it's not directly generated by the price processes. Right. And what we also want to assume is, well, that at time zero, the prices are deterministic. So we assume that the filtration at time zero is the trivial one. So means at time 0, we observe the prices. So the prices at time 0 are, mathematically speaking, constants. And at the terminal time, so the filtration at time capital T is just given by the sigma algebra on our probability space. All right. Okay. And then just this is our setting for, well, most of the course. And to make our lives sometimes simpler, and since it's basically rather realistic approximation of the world, is we like to assume often that the financial market, BS, is a finite market. This means that omega, so our underlying sample space, is given by a finite set. And this is, I mean, if you think about, so we have finite time steps, so this is okay. So there's anyway a finite number, and now we assume basically additionally that the values of the prices are also approximated by a finite number of possibilities. If you recall, for example, the binomial model, which we have already seen as an example, is okay, well, my price can in this binomial model go either up or down. So they're actually in the one period binomial model, we see actually our set omega has to consist only of 2 elements. All right. So this is finite, and to avoid unnecessary rotation, we also assume that we exclude all omegas and omega which have no positive probability. So we assume every omega, so in this set omega, has a strictly positive probability, right? So every element can really be happen on the real world. Okay. So that's okay. All right. Make it green. So this is sometimes a restriction, which is actually fulfilled by most of the discrete time models, which one really use to work with. Okay. Just to keep in mind an example. So most of the time, we just assume that the risky bond here, as a risk-free bond, is just given by an interest rate, and then it grows over the time in this way. So this follows the idea of saying we have an interest rate R, which is here, has to be assumed to be strictly bigger than -1, because we want that the risk-free bond is a strictly positive object. So we need to assume that the interest rate is at least strictly bigger than -1. And this is considered as the interest rate on the market. Right. But actually, most of the time, it's not very important what type of bond market we are considering. So let me call it usually B and not be specific about what actually it is. So as long as it's a deterministic process, it does not interfere with the probabilistic tools we have to use. Okay, so this is our underlying financial market. And there's a question, when wird das script? So there is actually, I updated yesterday the script. So if you want to have the current notes for this lecture, just look on my webpage. They should be available there. And at the latest tomorrow, I will probably update the whole chapter. All right. Okay, so now we fixed the underlying market, and now we want to first, of course, decide, okay, how can we trade on this market, right? Before we need to talk further about no arbitrage and so on. Well, the first thing is we need to agree what is actually the allowed trading or the admissible trading on this market. So first thing is we formulate what a trading strategy is in this market. So here, a trading strategy is predictable process. Right, so it has to be our D+1 valued, right? So it's a process, so we have a position, so we buy and sell each of these D+1 assets, so it's D+1 valued, it's predictable process, and we usually call it phi. And well, phi is it's a stochastic process with respect to our index t, and we have a position beta, which corresponds to the position in the bond market, and then we have a position alpha, which corresponds to the position in the de-risky assets. And now we make just a convention to keep our notation the following shorter. So the predictable process at time 0 is just the predictable process at time 1. And we will see in a second that this actually doesn't matter. So you could pick any, you can just also drop the definition at time 0 because it's not needed. So it doesn't, doesn't change anything. So let me discuss financially what this means here. So we have here our financial market. Okay, this is our time horizon, and we say we have here time t-1, t+1, right? And so what we do now is, and this is a way of bookkeeping, let's say. So we say the position we take at the tth period is labeled by phi t, right? So this is here the tth trading period. Sorry. Label t+1 trading period. Right. So because we start our time horizon somewhere here by 0, so the first trading period starts with 0. And so yeah. Right. And at the beginning of the t trading period, you pick the position t, and here you put t+1. Sorry, now I got the labeling right. Right, so at time t-1, the t trading period starts, and phi I denotes the positions you have in the market at time t-1. And you see, it makes sense, this is the assumption by predictability, that this here is ft-1 measurable. Right? And you also see at time 0, you pick actually the position phi 1. So the, well, position phi 0, which we introduced here, doesn't matter at all. Right. So what does it tells you here? So beta 0 corresponds to the quantity of the risk-free asset held during the teeth trading period. Right. And the same, just right. So phi is equal to beta and alpha. So this corresponds, just to formulate it for your notes, to the quantity of the D now, right? So this is an element in D, while this is element in R. D risky asset. Again, held. If you look in the literature there, you can also relabel the trading in the sets in different ways. So don't be confused if you see different definitions. But this is actually the one which is most consistent with the continuous time setting. Okay. All right. Okay. So now let us think, I mean, what is now, if we have these positions in the market, or follow this trading strategy, let me start with a new page. Okay. So what is now the value of the capital process we have? So what is the amount of capital we have or own at time, let's say t minus 1. So if at times t minus 1, the value, also called capital process, capital corresponding to a trading strategy phi. Well, what do we have here? So at time t minus 1, as we have just discussed, we have the position phi, which describe the quantities we hold in the risky and risk-free asset. So the total amount of money we have is given by, well, this vector multiplied, or taking the scalar product with respect to the prices of the risky asset at time t minus 1 and of the risky assets at time t minus 1, right? This is nothing else by definition, right? This, and well, just to write it out once at least, is the sum from 1 equal to 1 up to D, right? These are the D risky assets traded. In each of the risky asset, I have my position AI, so the quantity alpha I T. Yeah, so here's -1, we're saying -1 SI. Right. Okay. So now, if I hold this position over the T trading period, what happened is what is my capital at time at time T? Well, so now the price, so this is what happens here is the bracket is, so the price as T has changed to T, right? The same also is true for B, so BT -1 goes to BT. Right? So what does it mean for our, well, capital we have? Well, our capital, well, capital slash is now, well, this is just VT. And now I have the positions here. ST, right? So what we have now is this amount of money. Right? Okay. And now what we do is we rearrange our position. And this, I mean, now what we want to do is we want to rearrange our position here at, well, T, the T+1 period, trading period starts, and they're okay. How are we allowed to rearrange our positions? And this is actually formulated in the next definition, which tells us we only want to reformulate our positions in a self-financing way. So we are not willing to throw away money or adding money or allowed to add money. Right. So let us take your trading strategy, Y, T, be a trading strategy. Then we define here our value process. Associated, let's give it a name. So this is V, which is the process in time. This is associated, of course, to a trading strategy. Is given by, well, this is nothing else than what we have discussed already before, right? So this here, which is a nice color, orange, right? So this is what we turn into our definition of a value process. Right? So this is just telling us, okay, this is the amount of money we hold or have at time T. And now, well, we want also to make the convention because this is not, okay. So that's for t in t without t. And at the terminal time, well, this expression is not well defined, so we just say we are not rearranging our position again. So we just extend the value processor to capital T by the definition here, by saying we just take the position we had at the beginning of the trading period. So that's our terminal well we have. All right. So that's the definition of value process associated to a trading strategy. And now, well, we want to further specify how what kind of trading we are willing to consider. And this is the one. This is the first. The second one is phi. So this is a trading strategy. Is called self-financing. Color red. If we are not adding or throwing away money, then what does it mean mathematically? Well, it means that the amount of money we have at the end of the T trading period is equal to the amount of money we have at the beginning of the T plus 1 trading period, right? So we always just rearrange our positions, but we are not adding or throwing away money. For T equal to 1 up to time T minus 1. Right. Now so that's, where is this coming from? So this was coming from this idea here. Right. So what does this mean here? This is the capital and the end of the T period. And this is the amount of money, capital, at the beginning of the T plus 1 trading period. So now this is rather natural. So we are allowed to trade in a predictable manner, or so based on the information on the market, and we are only allowed to trade. And this, the assumption we make from now on basically is we are only allowed to trade in a self-financing manner, meaning we are not allowed to throw away money or adding money. Okay. Right. Oh, sorry. Let me formulate this also again for your notes. So self-financing means trader rearranges her positions and the beginning of each trading period without in a way that preserves the current value of her position. All right, so this is actually what I just have explained. So just that you have it in the notes, which because I think it's the rather important point. Yeah, because I mean, if you allow to trade in different ways, of course, the things which can come out might, well, lead to different definitions. All right. Let me make also some mathematically more rigorous remarks, which we will use later on. And well, they are about self-financing. So this is remark 3.3. So let us understand a bit better, I mean, what implication this self-financing condition has for a trading strategy. So first one is then this gives us an equivalent characterization of a self-financing trading strategy, which tells us, so if I have a self-financing trading strategy, phi, and I assume it's self-financing, as I said, this is the case if and only if I can express the value process at time t associated with this trading strategy phi as the initial value I had, so the initial capital I started investing in the market, plus the gains and losses I make in each trading period. Right? So I trade starting with the first period up to the time t, and in each trading period I have a position in the market, and then the price is involving so that's the SS minus ES minus SS. Right? So again, let me formulate this here. So what is this? These here are gains, losses made in the F period. Right. So self-financing means I can express the total value of money I have at time t as the sum of gains and losses I have made in each trading period up to time t. And here, I mean, this is, I mean, what if you recall this discrete stochastic integral, what we have seen before. I mean, here you see how discrete stochastic integrals come into the picture in mathematical finance, because the total value of the value process is just given by the discrete stochastic integral of our trading strategy with respect to the underlying price evolution of the market. Okay. So let me briefly prove this. Right. Okay, that's not too hard, but good to familiarize yourself with the definition of self-financing. So let's start with the self-financing trading strategy phi. So this is self-financing. Well, what do we have? So if I consider now the value process at time s and at time s minus 1, well, let me write out the definition. So the value process at time s is given here by phi at time phi s plus 1 multiplied with the price vector on the market at time s minus the same for time s minus 1. Right? So this is just plugging in the definition. And now we use the self-financing condition that this here, the first term is equal to phi at time s multiplied with the price vector at time s. And then keep the second term here unchanged. Right? And now we can use associativity of scalar products. So that's something else than this here. Right. Okay. And now how can we use this to get the formula we wanted? So if we consider now the value process of at time t associated with the trading strategy phi, well, we can use a telescoping sum argument. So we express this as starting with the capital at time 0, and then we add and subtract the changes of the capital in each trading period. This is just a telescope sum. And now we plug in the identity we just have derived. So that's nothing else than sum from 1, the s equal to 1 to t of, well, phi the gains and losses we make in the trading period. S minus 1 trading period. So this is S. Good. All right. So that's actually this direction here and this direction. It's an exercise for you. All right. So you see, self-financing leads to a very natural way to express the conditional, the value process of a associated to trading strategy. Okay. All right. Okay. Second remark I want to make is, well, if I have given initial capital, this means just a capital at time 0. Let's say B0, and this is just a real number. And I have a d-dimensional predictable process. say alpha given by this, again, alpha given for the times 1 to t. Okay, sorry, this is how we write it. And then this, well, predictable process alpha can be uniquely enhanced to self-financing trading strategy. So I mean, this looks rather okay, abstract and like, okay, well, why do you care? But it will make our proofs much easier in the future if we once agree on this statement, because this means if I restrict myself to self-financing trading, it's always enough to construct the positions of the risky, in the risky assets, and then because of the self-financing condition, the positions we need to take in the bond market or the bank account is already uniquely determined by the self-financing condition, and we don't need to care about it anymore. Right? So why? So this is, there's not much to prove. So in order to see this, so we can just iteratively define the position we have to have in the bank account in order to obtain a self-financing trading strategy. So if we want to know what is beta 1 has to be, well, we look at our self-financing definition. Let me scroll up. So if we look here of the condition self-financing, sorry, here, the self-financing, well, we know our initial capital, so we know what this capital process has to be at time 0. And we know all the positions except one, so we have an equality with one unknown object, so we just need to rearrange it. And this is what I'm doing here, is to say, well, the position I take is nothing else than beta 1 divided by beta 0, multiplied with the initial capital V0, subtracted the position I took in the risk in your risky assets. Okay. So okay, at time 1, so at time 0, I know what position I have to take, and now I need to define what is my beta at t plus 1. Well, same formula basically. So I take my value process at time t and subtract the position I took in the risky assets. For t equal 1 to t minus 1. Right. So this states that the feature, so the trading strategy here, is obviously predictable because the alpha t's are predictable. And now, by definition, how we constructed it, it's self-financing. So this is self-financing trading strategy. Okay. With the property that the initial capital for this trading strategy phi is exactly given by the constant B0. Okay, so if we want to construct some self-financing trading strategy, it's always sufficient if we construct the positions in the risky market, and then we can say, okay, by our assumption of self-financing, all the other positions are uniquely defined. Okay. Okay. So this is the way how we allow to trade, and now we want that the financial market here fulfills our no arbitrage principles. Right? We agreed already on these principles, which somehow assure that the market is a realistic model for a financial market. And well, these were 4 assumptions. The first one was the market efficient market hypothesis, which says, okay, the information are publicly available, so we cannot make any arbitrage by having extra informations. Second one was linear pricing rule, so the prices of 2 objects is just the linear combination of the price of each of the objects. And we have a completely liquid market, so there's unlimited liquidity, meaning we can buy and sell everything as we want it. I mean, these assumptions, the 3-1, are all fulfilled already by the definition of our market and the underlying trading, because we haven't put any constraints. The only thing which is really hard here to ensure is that there is no arbitrage. So the 4th assumption included in our no arbitrage principles are the no arbitrage assumptions. And well, here we need to be really careful to make sure that our market, we just have defined, is arbitrage free. Okay, so main task to ensure, and this our market PS is arbitrage free. Okay, because all the other assumptions, as I said, are basically fulfilled by the definition of our market. All right, so now let us make it mathematically precise. What does it mean to have an arbitrage or arbitrage opportunity? This is the next definition. So what we consider as only self-financing trading strategies, so trading strategy. Okay, so this phi is it's a trading strategy in time, and we call this trading strategy an arbitrage opportunity, so a way to make money without any risk. If well, first condition is the value at time 0 associated to this trading strategy is less or equal to 0. So we start with zero initial capital or even less. And at the terminal time, this trading strategy leads to a non-negative capital, right? So we are risking to lose zero capital because we started with zero capital, but in the end, we have a non-negative amount. Okay, and this is still doable. But the amazing part of a trading of the arbitrage opportunity is then that we are really able to make some money. Right? So with a positive probability, our terminal wealth or value or gain is strictly positive. Okay. That's arbitrage opportunity, right? This is somewhat too good to be true, so we want to exclude it at some point. And now, the obvious definition is a market, ES, is called arbitrage free if there exists no arbitrage opportunity. Okay, so again, and by our no arbitrage principle, I mean, these are actually the markets we want to consider before starting to talk about hedging and pricing of financial options. Okay. So the next step after we basically agreed on all the definitions, and I think you have basically seen all the definitions in the first chapter already, just now in a rigorous mathematical way. So we want now to understand under what conditions a market is arbitrage free. And the first thing would like to observe is that arbitrage is somehow a local property. So if I have a market with multiple time steps, what we will observe and prove in the next propositions is there is an arbitrage opportunity in one of the submarkets, right? The questions? Sorry, there's a questions. Okay. There's a okay. Wait. Sorry. Yes. Thank you for the question. So the question was about this formula here, and this is just wrong. Thank you. And let me correct it in the lecture notes as well. Okay. Thank you. Okay. So let me. So let us try to understand a bit better what arbitrage-free markets have to look like. And we start here with the observation that a market is arbitrage-free if and only if all the submarket, one-step submarket arbitrage-free. So let's consider here a market is arbitrage-free if and only if, let's restrict the market to one trading step. So if we just trade from n to, or n minus 1 to n. This is arbitrage free. Free for each n equal to 1 up to time t. No. Right. So a market is globally arbitrage free. So it's multi-step market is arbitrage free if and only if each individual trading period is arbitrage free. Right? So this cannot be that there's one period where we can make almost truly gains and one period where we almost truly lose, because I mean we could just not trade in the one where we lose. So here it has to be really arbitrage free for every step. Now, well, what do we have to show if we want to show that a market is arbitrage free? Well, we need to show that there exists no arbitrage opportunity. So let me give you an equivalent formulation of this proposition 3.5, and this is the one I'm going to prove. But well, this is obviously, equivalent. So what we going to prove, you could also like formulate it, of course, by proof by contraposition, but well, let me directly reformulate it equivalently and then prove the equivalent statement. So we consider here this market. Okay, this is not good here. This is here. So our multi-period market admits an arbitrage opportunity, so it's not arbitrage free. If and only if, well, there exists one trading period in which we can make arbitrage. So there exists, let's say, T star, which is one of our T trading period, and a random variable which is T star minus 1 measurable, so it's predictable, measurable, T plus 1 valued. It's a random vector, random variable, let's call it ether, such that, well, if we take this position at time, this position ether at time t minus 1, then we make almost surely no losses in this trading period, in the T star trading period. Right, so this is almost surely non-negative. And we make with a positive probability we make some gains. And so T minus 1, T minus 1, right? So that's up. So what this equivalent formulation here just means, I mean, the second condition here means is, well, there exists one trading period for which I can find an arbitrage opportunity, which is iter is here just a random variable because we have just a one-step model. Okay. All right, and well, this is now what we're going to prove. Should be fine in the next 15 minutes. Okay, that's the current formulation. So let's start with one direction. This is one. If I have an arbitrage opportunity, well, I can find a way. So I have an arbitrage opportunity on this multi-period market, and I can really identify now one trading period in which I make this arbitrage. So as the market admits an arbitrage, let's assume this arbitrage is called phi. And this is as usual. So arbitrage. And the corresponding value is well the okay. So far so good. And now let us construct this iter. So what we do is we pick the first time, we call this time t star, which is the smallest integers in our, so that's the trading period, the first trading period in which we realize the arbitrage. Right? This means at time k, so we know that our value process is non-negative, and with a positive probability, it's strictly positive. And we know that this actually is less or equal than t because phi is an arbitrage opportunity. So at the latest, by the definition of an arbitrage opportunity, we know that the capital T fulfills here the conditions in our definition of T star. And now we just take the first time where this is fulfilled. All right. And this means now we have two possibility at time t star. So note at time t star 4. So what can happen? So first thing is here the value process at t star minus 1 of phi is equal to 0. Or, and this is the probability of t star minus 1 of phi is strictly less than 0, it has to be positive. And this follows or by the minimality of t star. Right. Because otherwise, I mean, what none of these conditions would be, I mean, none of these cases would be true. Already t star minus 1 would fulfill the definition of t star. So we haven't picked the right t star. Okay, let's now consider T1, the case 1. And let's see how we can get an arbitrage. So if we consider the value process here, let's take the position fees phi at time t star. So this is what we pick at the time t star minus 1. So that's here. And now in this t trading period, our gains are given by this quantity here. Right. But this is nothing else than the value process at time t star of phi minus, I mean, if you think about the self-financing condition, so this is easy to see by self-financing. Right here, it helps to think about these value processes as discrete integrals. And now, since we're in case 1, this is just 0. So that's the value at the value process at time t star of phi, meaning random variable, let's call ether, define ether as phi t star. This is by definition, it's f t minus star minus 1 measurable. And let's label this as 3.2 to be consistent with the lecture notes. So this ether fulfills our condition. (3.2). Okay, right. So in the first case, we found actually our single step arbitrage, and now we just need to handle the second step. Which okay. Put it up again. So this is the second case. So how do we find our ether now? Well, we just define ether to be, again, phi at time t star, right? This is the arbitrage opportunity we want to work with. And now we restrict it to the case that we only take this position if the value process at time t star minus 1 with respect to this trading strategy was negative. And otherwise, we're not trading in the market. Well, I mean, this is with a positive probability that we really follow the arbitrage opportunity phi. Of course, this is ether is t star minus 1 measurable, right? Because the trading strategy phi is predictable, and this event here is ft minus 1, ft star minus 1 measurable. And let us see if we also have this arbitrage condition fulfilled. So let's calculate here the gains we make in this t star period. Right. Again, let's apply the self-financing condition. Right. And now we know, well, if we are not trading, we're 0 anyway. So we can restrict this to the event that this here is strictly negative. and well, this is by assumption non-negative, so you can estimate it from below by the second term here. So that's -1 by condition of the event that this is actually negative, strictly negative. So this is actually strictly positive, sorry. Okay. All right. So again, is an arbitrage for the T-star trading period, and this means this is an assumption we had to check. All right. So okay. This was one direction. Now we need to check the other one as well. So let us assume that there's a T-star and an ether be such that this condition 3, 2 volts. Let me show it to you again. So this means ether is a T star minus 1 measurable random variable, which takes values in RD plus 1 and is an arbitrage in this T star trading period. So we make at least, I mean, almost surely no losses in this trading period. And with the positive probability, we make some gains. And now we just need to extend this local arbitrage to a global one. So let's extend this to a predictable process, this ether to a predictable process by, well, defining the position in the risky asset by that's not good. Oh. That's not good. Okay, the proof was correct, but zip. Sorry. Okay, that's not good. Because this should be only T. Yes. Okay, I will correct this one, but you can think about this, why this is correct. I will correct this at the beginning of next lecture and redo the proof. The issue is why I have to cross out these terms here is actually I don't need to do this. Okay, I think I can self myself. Sorry for this. I was confused because I mean there's a mistake in the script, but this should be not a problem. So what we do is we say this is ether 0 to 1. To D, and now we define alpha to be the vector from 1 to D and 0 otherwise. So if T is equal to T star, and otherwise we just keep it to be 0. And so this is just our vector. And now We can extend this to a self-financing trading strategy by our remark we just made. I mean, that we can, if we have the risky position, the risk-free one is always fulfilled. So this here is self-financing. And the initial capital is just given by 0. Now, what we observe by calculating the terminal value of the value process with respect to phi, it's nothing else than ether okay, it's not clear that my save works. All right, that's all for a time t star. Times c star right, and this implies that phi is an arbitrage opportunity. Okay. I will revise the proof a bit at the beginning of the next lecture because there was some, I mean, there are some typos in the proof in the lecture notes which I have to fix. I try to do it here now along the way, but well, this is then of course not as clean as it should be. So I will comment on this one at the beginning of next lecture. All right. Are there questions? All right. Then I wish you a nice day and thank you very much.